Hi guys, today is March 28th and we're going to do the radius of convergence, and it's going to be the first day of it. We're going to spend a couple days on this. Okay, so today's the 28th. Um, just so you know, we're kind of ahead of where we were last time I taught this class. Last time this was done on March 30th, so this is good. Okay, we're still in good shape. All right, guys. And last time everybody passed the BC calculus exam. Okay, so we're doing good. We're staying on top of everything. We're okay where we're at. All right. I just wanted to reassure you and let you know we're doing okay. All right. All right, so the first example is this: find the value of x for which the equation is an identity. Now, what identity means is that this is true, okay? So what values of x is this true? Well, if you look, there's a couple ways to look at this. One way, you could look at this and go, okay, I'm multiplying by x minus 2 each time, right? So 1 times x minus 2 is x minus 2. X minus 2 times x minus 2 is x minus 2 squared. X minus 2 squared times x minus 2 would be x minus 2 cubed, and so on, right? So that would mean this is a power series, which means it's a geometric series, okay? And then our r would be this x minus 2. Okay, so that's one way to look at it. I want to look at it, maybe you might think, oh, that's a little more complicated the way I'm going to look at it, but I want you to be able to see it both ways, okay? So this doesn't look like the form that we want, right? This first term is 1. Okay, so this we should rewrite, we should make that 1, and then we need 1 minus something down here in the denominator, okay? So I want to rewrite this sum so it looks like 1 over 1 minus r, or a sub 1 over 1 minus r, okay? So what I'm going to do to this is I'm going to negative 1 over x minus 3. What I'm going to do is I'm going to multiply it by negative 1 over negative 1, okay? And then that would give me 1 over, and then this would be negative x plus 3, okay? Or 3 minus x. But there's not a 1 right here, right? I need it to be a 1. Well, I could break this 3 up into 1, okay, plus 2. Or this becomes 1 over 1 minus, and then x plus 2. Now that's 1 and 1 plus 2 still makes this 3 right here, and we still have a minus x. That's going to allow me to factor out a negative, and then that would be 1 over 1 minus parenthesis x minus 2. And there we see the r, right? It's x minus 2. So this is just a way of rewriting this, okay? All right. So the original question was find the values of x for which the equation is an identity. Okay, so we needed our r. This is our r right here, okay? Because this is only true if r, the absolute value of r, is less than 1. And I should say this, our r is x minus 2. So we can get the x minus 2 from this. We can also get the x minus 2 by looking, okay, we're multiplying by x minus 2. So there's two ways to figure this r out, okay? I just want to make that really clear. So this r is x minus 2. So that'd be the absolute value of x minus 2 is less than 1, okay? That means that x minus 2 has to be in between negative 1 and 1. And then we're going to solve this, okay? So adding 2 to this, we get 1 is less than, x is less than, and then adding 2 would be 3. So this identity is true only for these x's. It's only true. This function right here, negative 1 over x minus 3, and this infinite series here is only true when x is between 1 and 3, okay? Now, you've heard me say this in class. I've said something about the radius of convergence, okay? And that's where this comes in today, okay? Is we're going to talk about the radius of convergence today. So what is this radius of convergence? Well, the interval is from 1 to 3. That's a distance of 2, okay? So from 1 to 3, that's a distance of 2. Or how did I figure that out, okay? The distance between those two is 3 minus 1, which is 2, okay? The radius would be half of that, okay? So the radius of convergence I'm just going to write this. Radius of convergence is it's always going to be this, the distance divided by 2. So that's going to be 2 divided by 2, which would be 1 in this case. Okay, so that would be the radius of convergence in this problem. Okay, so it kind of looks like this. All right, if you talk about like a number line, okay, let's say right here's 1, and then right here is 3. Right here at 2 is the center of convergence. Okay, so that's why we're using this term radius of convergence. Okay, the center of the convergence is 2, and you can tell that by we've shifted it over x minus 2, right? We've shifted over the regular power series 2 to the right. Okay, and so it has a radius, okay, of where it converges, 1 to the left of 2 and 1 to the right of 2. That's why it's between 1 and 3. Okay, so that's why we call it the radius of convergence. Okay, all right, so I'm going to slide this up a little bit. Okay, and I want to read this. Okay, since the power series is a good approximation only on its interval of convergence, we need to develop some tools to find the interval. Okay, we always check the interior of the interval first. Okay, so we're going to, a lot of times, what the geometric series is really important because it allows us to determine this radius of convergence. Okay, a lot of times that's where we're going to get in between two numbers. Okay, um, then we're going to check the endpoints for convergence, and we're going to learn that in I think it's the next. We have 2 lessons for radius of convergence, and then we talk about endpoints, and we'll do it there. Okay. And there are several useful tests. These are all tests that I've already taught you. That's kind of nice. Okay. Each test has conditions that must be checked before the test can be applied. All right. So let's slide it up a little bit more. Okay. So we have this one, right? The nth term test for divergence. If the limit as n goes to infinity of the a sub n term, the nth term, and it doesn't equal 0 or fails to exist. Now, fails to exist means it's negative infinity or it comes out to be infinity. That would mean it fails to exist. Okay. Then sigma n equals 1 to infinity of a sub n diverges. So the series diverges. Okay. All right. And then we have the geometric series test. Geometric series is the form of this form. That's what we just saw in the above example. It converges only if the absolute value of r is less than 1. And this is what it converges to. The sum, if we were able to add them up, would be a, which is the first term. Okay, let me write that first term. Okay, based on your sigma notation, what you're putting in for n, that first term would go right there over 1 minus r. Okay. All right, let's do some more problems. All right, so we did have one more test I want to talk about before we get into the examples, okay? It's the direct comparison test, okay? We need to look at it, and we've done this before again, okay? But what we want to do is we're trying to prove or show the convergence for this series a sub n, okay? Now, if we want to compare it to a bigger one that converges, okay, then that means the one that we're looking at also must converge. So if we can compare it to a bigger series, okay, that's always bigger, then the smaller one has to converge also. If the bigger one converges, the smaller one converges. Or we want to compare it to a smaller one that diverges, okay? A smaller one that diverges. Because if the smaller one diverges, then the one we're trying to find must also diverge, okay? If it's bigger, if it's bigger than the one we're looking at and converges, then it converges, okay? All right, so this one's going to be used a lot to show that it converges. All right, and then another one is a very useful series to compare it to is the Maclaurin series for e to the x. So recall that e to the x is equivalent to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot 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 plus x to the n over n factorial plus dot 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 equals sigma n equals 0 to infinity x to the n over n factorial. Okay, so this is going to be an important one because if you have x to a power over n factorial, it's of this form. Okay, so we're going to be looking for something raised to the n power over n factorial. Okay, if we have that, okay, if we can rewrite it so it looks like this or similar to this one, then we can compare it to this one. Okay, all right. All right, so let's go to this next example, example 2. All right, for example 2, use a comparison test to show that the series converges for all x. And I neglected to say this, for this one up here, this e to the x, this converges for negative infinity to positive infinity. So the interval, this works for every single x, not just a limited number of x's, okay? It doesn't work just on an interval, it works on negative infinity to positive infinity. Well, I guess that's an interval too, though, okay? All right, so I want to take a look at this. Okay, I want to rewrite this one. Okay, sigma n equals 0 to infinity x to the 2n over n factorial plus 2. All right, this kind of takes on this form. Okay, the plus 2, we don't have that over here, right? Okay, but what we want to do is we look at this and we go, okay, this could be rewritten as n equals 0 to infinity. And this numerator could be rewritten as x squared to the n over, and then n factorial plus 2. All right. And then that gives us something to compare it to. So if we compared it to x squared to the n over n factorial, okay, we would be able to tell, okay, since this is plus 2, all right, then this one's going to be smaller than this one, right? Okay, we're going to put an x squared here. Okay. All right. So let's just take a look at this series. Okay. So let's take a look at sigma n equals 0 to infinity of x squared to the n over n factorial. Okay. So that's this series up here. Okay. It's just instead of having x, what do we have in the x spot? We have x squared, right? So we have an x squared right here instead of x. So that means this is equivalent to e to the x squared power. Okay. So what that means is it converges, right? So sigma n equals 0 to infinity, okay, x squared to the n over n factorial converges to e to the x squared for all x, because e to the x converges for all x, okay? So we have one that's bigger, that's converging, right? Because this one's going to be bigger than this one. So that would mean that x to the 2n over n factorial plus 2 is less than or equal to x to the 2 n power over n factorial. Because if you compare denominators, this denominator is going to be bigger, which makes the overall value smaller, right? Okay. And so we know this one's smaller, and we know this one is converging, right? Because this one is equal to x squared to the n over n factorial. Therefore, we know this one must converge for all x, okay? So therefore, we've got it. Therefore, henceforth, I always like to say that, henceforth, okay, or therefore. Sigma n equals 0 to infinity of x to the 2n over n factorial plus 2 converges for all x, and then we have to state the test that we're using, and we're using the direct comparison test. So by the direct comparison test. Okay, and that's example number 2. All right, for this next part of example 2, okay, for part B, what we need to look at is, again, we know that sigma n equals 0 to infinity. This is a fact you should know, okay? X to the n over n factorial is always going to equal e, okay? So comparing this one, this looks like what's in the x spot is 2, and then we have n factorial. So it's this plus 7 that makes it not different, right? That is not perfectly e or a version of e, okay? So what do we need to do? Okay, so we need to establish what 2 to the n over n factorial, because it's taken on this type of form, right? So what do we know? We know that sigma n equals 0 to infinity of 2 to the n over n factorial. Okay, so, and you know what? I wrote this wrong. This should be e to the x. That should be e to the x up there, okay? Not just e. Okay, so right here, what's in the x spot right here? Okay, well, it's the 2, right? So that means this converges to e squared, okay? So this converges to e squared. And this is what we want to compare this one to, okay? So what do we know about this one? These almost look the same, but this one has a denominator with plus 7 in it, right? So the plus 7 is going to actually cause this denominator to be bigger, which is going to cause this fraction to be smaller, which means this one must be bigger, right? So we have 2 to the n over n factorial plus 7 is less than or equal to 2 to the n over n factorial, okay? And we do know that this one's going to be smaller than this one, and we know this one's converging, okay? Therefore, this one must converge by the direct comparison test, okay? So, and because this one converges for negative infinity to positive infinity, this one has to converge for negative infinity to positive infinity, which means this one has to converge from negative infinity to positive infinity, which means for all x, okay? All right, so therefore, okay, the sigma n equals 0 to infinity, 2 to the n over n factorial plus 7 converges for all x by the direct comparison test. We always have to state the test we're using. And now that's finally it for example 2, okay? Now for some review on some definitions, okay? If the series sigma absolute value of a sub n of absolute value converges, okay, then the series converges. We say the series converges absolutely. So if we take the absolute value of the nth term, okay, and we see that that series converges, then the series converges absolutely. Okay, and if this is the next theorem, if that converges, then we know the original series must converge. Okay, all right. Now, if the absolute value diverges and the original series converges, then we would say that the original series converges conditionally. Okay, and we've gone over all that back when we did improper integrals and some infinite series back in the last unit. Okay. All right, for example 3, we want to show the series converges absolutely, which means I'm going to have to take the absolute value of this nth term, right? Okay, so we want to write sigma n equals 0 to infinity of the absolute value of 2 times sine of x raised to the n over n factorial plus 3. Okay, and then that's equal to sigma n equals 0 to infinity. Okay, now when we take the absolute value of this, okay, we take the absolute value of the numerator and the absolute value of the denominator, and the absolute value of the denominator is n factorial plus 3. Well, n is starting at 0 and then getting bigger and bigger. This is always going to be positive, so we really don't have to put an absolute value on the n factorial plus 3. So I'm going to write that without absolute value because we don't need it. We only need it when it's going to be negative, okay? All right, so then the absolute value of the numerator, okay? But for the absolute value of the numerator is a product. So it'd be the absolute value of the two things we're multiplying together. The absolute value of 2. Well, we don't need it for that because it's already 2, right? So it'll just be 2. Now, the absolute value of sine of x to the n, we need absolute values around that. But since it's being raised to the n, really, we just have to take the absolute value of sine of x raised to the n. So that'd be times the absolute value of sine of x raised to the n power. Okay. And then one of the properties of sigma notation is this is a constant. It's kind of like integration, okay? Because integration is really sigma, okay? So this 2 can get pulled out in front of the sigma, and it would be the same because if you wrote all the terms out for this n equals 0 to infinity, all of them would be being multiplied by 2, which means you can factor it out of each term, which means you could pull it out of the sigma, okay? So this would be 2, 2 sigma n equals 0 to infinity of the absolute value of sine of x, because sometimes sine is positive and sometimes is negative. That's why we need the absolute value over n factorial plus 3. Okay, so I've I've talked about this a little bit, okay, already, but what we want to compare this to, all right, is this, okay? When we have sigma n equals 0 to infinity of, let's say x to the n, right? Or something here, right? Over n factorial. Something raised to the n over n factorial, that's always going to converge to e to the x, or whatever the base is right here, okay? So if this is a 2, or it's x plus 3, or it's 5x, whatever this might be, that's what goes right here. All right, so that's why we want to, if you look at this, okay, we're raising something to the n power over n factorial, right? So we want to compare this to e to the x. So that's kind of giveaway of like, we're going to compare it to that one, okay? Maybe you're already picking up on that. I wish I could see your face and know and just look and see, but we just can't do that right now, okay? All right, so what are we going to compare this to? Well, we're going to compare it to one of these, okay? And I know that if I compare this, I know this sine of x, okay, the biggest sine x could ever be is 1, okay? So if I look at this, the absolute value of sine of x raised to the n power over n factorial plus 3, I know that that is always going to be less than 1 to the n over n factorial. Now, what's great about this? I know this one converges because of this idea up here, okay? Because in the x spot is 1, okay? So I know this one is always, this is always going to be true, okay? And then I need to say this, okay? So I need to say this, and then I need to show that this one's convergent, okay? So this one, so sigma, or I need to show this one converges, not this one. Okay, sigma n equals 0 to infinity of 1 to the n over n factorial converges to, and what would it converge to? Well, it'd be e to whatever this is, right? So it converged to e to the first, or just e, okay? All right. So what do we know? We know that this one, which is the same as this one, right? This series right here, that it must converge, right? So sigma, because we're comparing this one to this one's bigger and it converges, therefore this one converges, which therefore this one converges, and all three of these are the same, okay? So this and this are the same thing, right? That's why the equals are important. So sigma n equals 0 to infinity of the absolute value of 2 times sine of x raised to the n over n factorial plus 3, close that absolute value. This one we know converges by the direct comparison test. And so we know that the original series, sigma n equals 0 to infinity of 2 times sine of x raised to the n power over n factorial plus 3 converges absolutely. Converges absolutely. Because this one converged, right? And we say if the absolute value one converges, then we say the original series converges absolutely. Okay. All right. And that's example number 3. All right. So the next thing I want to do is I want to review this thing called the ratio test. And this is the most often used on the AP exam, okay, to determine the convergence of a power series. Okay. So let this be a series, right, with positive terms, and limit as n goes to infinity, a sub n plus 1 over a sub n. The absolute value of that, right, is equal to L, okay? And if this number L is less than 1, then the series converges, okay? Now, the big idea, like I'm going to tell you, like this is how I remember this, okay, is that for a series to converge, the n plus 1 terms, your terms have to be getting smaller and smaller and smaller and smaller, okay? So if this a sub n plus 1 term is smaller than a sub n, right, then let's say, let's do numbers. Like if this was 2 and this was 5, right, then that would come out to be a number that's less than 1. So if we do this and this is if we come out with less than 1, that would mean our numerator is smaller than our denominator, okay? Which means the terms are getting smaller, right? Which that's why this one converges, okay? That's kind of a nutshell of why this works, okay? If it's bigger than 1, okay, then that would mean these terms are bigger than these, and that would mean it's diverging, okay, because the terms have to be getting smaller for it to converge, okay? And then if L equals 1, we have to use some other test, okay? All right, and we've gone over this. We did the ratio test before. What's the difference between this, what we're doing now, and what we're doing before is we have these power series, okay, and it's not just numbers and ends. It involves also the x's, okay? All right, so that's what's a little bit different about this. And I actually wanted to say something more about this. Sorry, guys. All right. When do you want to use it? I mean, what features of the series do you look at and go, oh, I should use the ratio test, right? And I told you this before, but doesn't hurt to say it again, okay? We want to use this. We want to look to using this ratio test, okay, when we have something to the nth power or, okay, we have n factorial. Okay, so that's when we want to look to using this, because what's going to happen is terms are going to cancel out. Okay, if we have nth, because we're doing a ratio here, we're dividing, right? If we have something to the nth, okay, power and n factorial, stuff's going to cancel. Okay, that's why we want to use this. All right, for this next example, example 4, we're going to do part A, part B, part C, and part D. okay? And what I want you to look at is the different things that can happen when you try to find the radius of convergence, okay, for these different series, okay? All right, so what we want to do for this one is series, right? And we have an nth power, so you should be thinking, okay, ratio test would be a good one, okay? So we're going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, that's equal to the limit as n goes to infinity of, okay, so it's going to be 3x minus 2 to the n plus 1 power over n plus 1. Okay, so this is going to wind up being a complex fraction. Okay, so I'm going to come up here a little bit. All right, so 3x minus 2 to the n plus 1 power over n plus 1, big, huge fraction bar. Okay, and then it's going to be 3x minus 2 to the nth power over n, big, huge absolute value. Okay, now this is a fraction divided by another fraction. Okay, we can rewrite this as the limit as n goes to infinity of the absolute value of 3x minus 2 to the n plus 1 power over n plus 1. And then we're going to multiply by the reciprocal of this, right? So it's going to be n over 3x minus 2 to the n power. All right, so we're going to rearrange numerators and denominators to get kind of like, I don't want to say like terms, but like I want to put this one in the numerator and this one in the denominator, okay? So we did this before, okay, when we did the ratio test the first time. So absolute value of 3x minus 2 to the n plus 1 over 3x minus 2 to the n, and then times n over n plus 1, close the absolute value. All right, and then this is going to become, okay, so these bases are the same, so we're going to take this exponent and minus this one. So it's just going to be 3x minus 2 to the first power, right? So this is equivalent to the limit as n goes to infinity of the absolute value of 3x minus 2 to the first power, right? Times n over n plus 1. Okay, so now what we're going to do is we're going to break it up. So then this is equivalent to the limit as n goes to infinity of the absolute value of 3x minus 2 times the absolute value of n over n plus 1. Okay, as n goes to infinity, there's no n here, right? So it's just going to come out to be the absolute value of 3x minus 2. Now this one is where our n's are, right? So as n goes to infinity, these are going to, so we look at the magnitude for this, right? So it's n over n. So that one's just going to go to 1. So this winds up being just simply the absolute value of 3x minus 2. But we're supposed to get a number out of this, right? That's what we did last time when we did this, okay? Well, no, not for these because we have x's involved, right? Okay, so what we know is, all right, we know that this is going to converge, but it's based on what this is, right? And we are going to know it's going to converge when this is less than 1. So I'm going to write here the series converges when the absolute value of 3x minus 2 is less than 1. So it has to meet that condition for it to converge, okay? I'm going to slide this up a little bit. Okay, so what does this mean, okay? So this means that the absolute value of 3x minus 2 is less than 1. What that means is that the 3x minus 2 has to be in between -1 and 1. So we write -1 is less than 3x minus 2 less than 1. We're going to add 2. So that's going to give me 1 is less than 3x, which is less than 3. And then what we're going to do is divide by 3. So this becomes 1/3 is less than x is less than 3/3, which is 1, right? Okay. All right. So what this tells us is this series will converge, but only when the x value is between 1/3 and 1. Okay. All right. So what's the distance between these, right? What's the distance? This from 1/3 to 1, that would be a distance of 2/3, right? Right. So the distance between these would be 1 minus 1/3 or 2/3. Half of that would be 1/3. So the radius of convergence is 1/3. Okay. All right. So by the ratio test, that's what we're going to say. Okay. By the ratio test, comma, the series that we were looking at, right? Sigma n equals 1 to infinity of 3x minus 2 to the n over n converges. So it does converge, but it's for 1/3 is less than x is less than 1. Or you could write this also in interval notation. So you could also write it as 1/3 comma 1 like that. Okay. You could write it either way. Inequality, interval notation, same thing. Okay. All right. So that's part A. I want to look at another one where we're finding the radius of convergence and just look at this as, what test or what do we use to go about doing these. Okay. All right. So next one. All right, so looking at this one, again, find the radius of convergence for the series, okay? N equals 0 to infinity, okay? X plus 3 to the n over 2 to the n. Now, there's a giveaway here. We're raising the numerator to the n power and also the denominator to the n power, okay? So that could be rewritten as sigma n, my sigma looks kind of funny there, okay? Sigma n equals 0 to infinity, right? And if these are both being raised to the n power, we could rewrite that as x plus 3 over 2 raised to the n power. And what you should be recognizing is this is a geometric series because this is the thing we're multiplying by, right? X plus 3 over 2, okay? So automatically we know that sigma n equals 0 to infinity of x plus 3 to the n over 2n, 2 to the n, not 2n, okay, 2 to the n is a geometric series with r equal to x plus 3 over 2. Okay, and by the geometric series test, sigma n equals 0 to infinity, x plus 3 to the n over 2 to the n will converge will converge when, and how do we know when a geometric series converges? When the r, right, x plus 3 over 2, when the absolute value of x plus 3 over 2, the absolute value of that is less than 1, okay? So this is going to allow us to find that radius of convergence. So The ratio test will sometimes help us to find the radius of convergence, okay, or the interval of convergence, and the geometric series test. So the ratio test and the geometric series test are really important tests because they'll tell you where this thing is converging, okay, for what x values they're converging. Okay, so what we have to do is solve this, right? So it's going to be -1 is less than x plus 3 over 2, which is less than 1. I'm going to multiply the left, the middle, and the right by 2. So -2 is less than x plus 3, which would be less than 2. And then subtract 3 from the left, the middle, and the right. So that'd be -5 is less than x is less than 2 minus 3, which would be -1. Okay? So we know this series converges, but only when x is between -5 and -1, okay? Okay, so we've already said that converges. Okay, so sigma n equals 0 to infinity x plus 3 to the n power over 2 to the n converges for -5 is less than x is less than -1. And the radius of convergence is, okay, so what's the distance between -5 and -1? So -1 minus -5, right? So -1 minus -5 is 4, and half that would be 2. So the radius of convergence is 2, okay? All right, so let me write this, okay? The distance between these, that would be the entire, that'd be like the diameter of convergence, okay? You can't think of it like that. It's the diameter of convergence, okay? It'd be -1 minus -5, right? And that would be -1 plus 5, which is 4. Okay, so the diameter of convergence, nobody calls it that, but the diameter of convergence is 4, so the radius of convergence would be half that, which would be 2. Okay? All right, so that's the next example, okay? So let's go look at another one, okay, and see what happens. And we're doing 4 different things. So these aren't 4 of the same things, okay? The same thing's happening, okay? It's 4 different things. So first one was ratio test, and we were able to get the radius of convergence that way. This one, we were able to use a geometric test to find the radius of convergence, okay? And then a couple special ones for the next 2, okay? So let's look at the next one. All right, so for this next example, again, we're going to find the radius of convergence for the series. And something I want you to realize is that the only way to find the interval of convergence is either the ratio test, we can use the ratio test to do it, or the geometric series test. Those are really the only 2 tests that will allow us to determine what x values that the series converges for, okay? So let's take a look at this one, okay? This is not going to be a geometric series automatically because of the factorial, okay? And so let's take a look, let's use the ratio test to determine what's going to happen here, okay? So we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so that's the limit. By the way, we want to write this, okay? The limit as n goes to infinity of x to the 2 times, well, let's just go ahead and write x to the 2 times n plus 1 over n plus 1 factorial. So we need to put parentheses around the n plus 1 factorial, and then big fraction bar, and then x to the 2n plus 1 over n factorial, and then big, huge absolute value. All right, so now we're dividing this, right? So this is going to be written as, I'm going to come off to the right side here, the limit as n goes to infinity of, this is going to become x to the 2n plus 2 plus 1, right? So this is going to be x to the 2n plus 3 over n plus 1 factorial, and then times, and then this one's going to be the n factorial is going to be on top. So n factorial over x to the 2n plus 1, close the absolute value. Rearranging these, I want to put these two together as one fraction and then these two. So this is going to be my numerator, this is going to be my denominator. And for this one's going to be my numerator, and this one's going to be my denominator. Okay, so this is the limit as n goes to infinity of the absolute value of x to the 2n plus 3 over x to the 2n plus 1 times n factorial over n plus 1 factorial. Okay, now what happens on this one? Okay, so we have x to the 2n plus 3, and we're going to subtract 2n plus 1 from this power, right? So 2n minus 2n, those are going to go away. 3 minus 1, that's going to be 2. So this winds up being the limit as n goes to infinity of x squared times, okay, now this is n factorial over n plus 1 factorial, right? So this one, remember, I'm going to do this in red. This one is n times n minus 1 times n minus 2 times dot, 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 right? And then this one would be n plus 1 times n minus 1 times n minus 2 dot, dot, dot. So the n all the way into n factorial, and this would be n factorial. So they're going to cancel, and you're left with 1 over n plus 1. Remember we did that before, okay? Now, n's always positive, so we really don't need the absolute value on this one. We are going to take the absolute value of x squared, but to take the absolute value of x squared, that's the same as taking the absolute value of x and squaring it. Okay, so this is the limit as n goes to infinity of the absolute value of x squared times 1 over n plus 1. Well, what happens as n goes to infinity? As n goes to infinity, this doesn't have x, so it's going to stay the absolute value of x squared, but this denominator is going to get bigger and bigger and bigger. So this fraction is going to get closer and closer and closer to 0. So as we go to infinity, this becomes 0. So we have 0 times the absolute value of x squared. Well, anything times 0 is going to be 0. So this is equal to 0. So what does this tell us, right? What the heck does this tell us? It's 0, right? Well, what do we know? If it's less than 1, if this limit is less than 1, okay, then that tells us that this series converges, right? But for what x is, I didn't pick up x's this time, right? So we can't say x is less than 1 or something like that, all right? What this means, because we got a value here that's less than 1, it's going to converge for all x's. So it's not dependent on a certain interval of x's. It's all x's this is going to converge to, okay? So we can write, since the limit as n goes to, as n approaches infinity, of the absolute value of a sub n plus 1 over a sub n is less than 1, right? We know that this series, n equals 0 to infinity, x to the 2n plus 1 over n factorial converges by, let's slide this up a little bit, by the ratio test. And the series n equals 0 to infinity, x to the 2n plus 1 over n factorial converges for all x values. Or you could also say for negative infinity to positive infinity. You could write it as an interval, okay? All right. So what's the radius of convergence? Well, if we're going from negative infinity to positive infinity, the half of that would be still infinity, right? All right. So it's like, okay, 2 infinity divided by 2, okay, it's infinity, right? So the radius of convergence, okay, the radius of convergence is infinity. Okay, and that's the write-up we need to do to write this up for the AP exam, okay? All right. Okay, so let's take a look and see what happens on the next thing. Something different is going to happen on the next one too, okay? So let's go to the next page. All right, for this final example, find the radius of convergence for this series, okay? So it's, again, as soon as they say radius of convergence, we should be thinking, okay, ratio test or convergence test, okay? So we're going to look at the ratio test for this one because this one's definitely not geometric because of the n factorial, okay? So we want to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. That's equivalent to the limit as n approaches infinity of the absolute value of, okay, so this is going to be n plus 1 factorial, right? N plus 1 factorial times x minus 3 to the n plus 1 power over n factorial times x minus 3 to the n power. Close the absolute value. Okay, so what's this equivalent to? Well, this would be equivalent to the limit as n approaches infinity of, and I would do n plus, I'm going to separate this into two fractions, okay? We'd have n plus 1 factorial over n factorial times x minus 3 to the n plus 1 power over x minus 3 to the n power, close the absolute value. Okay, so this would be n plus 1 times n minus 1, right? So this is just going to wind up, this part right here is just going to wind up being n plus 1. So this is the limit as n approaches infinity of the absolute value of n plus 1 times, and since the bases are the same, we're going to take this exponent and minus this one, so we'd be left with just x minus 3 to the first, or just x minus 3. Okay, since n's going to infinity, we really don't need absolute, like the absolute value of a product is the absolute value of this times the absolute value of this. But since n is going to infinity, this will never be negative, so we don't need the absolute value for this one, okay? So this would be, again, the limit as n approaches infinity of n plus 1 times, now this one, depending on what the x is, this could be negative, this could be positive, right? So we do need the absolute value on this one. So absolute value of x minus 3. Okay, so now what happens as n goes to infinity? Well, n goes to infinity, n plus 1. This is just going to get bigger and bigger and bigger and bigger and bigger. Regardless of what this is, we're multiplying by a number that's bigger and bigger and bigger and bigger and bigger. So what's going to happen is this is going to go to infinity. So this is equal to infinity. Okay, now what the heck does that mean, right? Okay, so that value infinity, well, that's bigger than 1, right? Okay, so it's definitely bigger than 1, which means the series diverges, right? So then we can write this, since the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is greater than 1, right? Because infinity is bigger than 1, okay? The series okay, which is the series we're talking about above, right? Yeah, actually, I'm going to write the series. Because what series are we talking about when we just say this series? I don't think we're being specific enough. Okay, actually, I'm going to take out the too. So what do we know? We know the series that we started with, right? Sigma n equals 0 to infinity of n factorial times x minus 3 to the n diverges by the ratio test. Actually, let me capitalize ratio and test. That wouldn't matter, okay? That's just me being fuddy-duddy. Period, okay? Now, what's the radius of convergence? Well, okay, if it diverges, there is no radius of convergence, right? So we would just say the radius of convergence is 0, okay? So if this was like a Taylor series or something like that, okay, and it's centered at this X value, right? Okay, so the only thing that would be true is it would be the same. Okay, so there's no radius of convergence. There's no radius of where this thing is converging on. Okay, but if it was how am I going to say this? It's only going to be the same. You know, that series, the Taylor series and the function would only be the same at that one X value, okay, that that you have it centered at, and that's it. That's what would be happening here, okay? All right. Hopefully that makes sense. Sorry, I kind of stuttered there for a little bit. All right. Anyway, so that's radius of convergence day 1. We'll do day 2 and for the next lesson. Okay, and then we'll do endpoints of convergence later on. Okay. All right. So I hope you guys have a wonderful day. Take care. Can't wait to see you guys. All right. Bye-bye. Okay, so one last thing I forgot to tell you guys. Okay, so to our assignment sheet. Okay, I want us to do the radius of convergence day 1, okay, and it's assignment 11-5, and it's page 515, 1 through 21 odd, okay? And again, this is helping me keep track of what we're doing, okay? So March 28th, all right? All right, so now, goodbye, guys. Take care.